Okay, good morning. So today we're talking about random numbers, producing them, using a computer, and also exploiting them for integration, especially in multidimensional integration. What's called using the method of Monte Carlo. So as you know, there are no real way, there's no real way of producing uh, random numbers, really real numbers out of a computer. Because everything in the computer is deterministic, but somehow we can produce pseudo random numbers in some way. We start with a seed and apply for it or upon it many manipulations, and it will appear eventually as it came from some distribution. So we're not talking. We will not talk about this. We will assume in this recitation that we know how to produce using the computer some pseudo-random or random variable which distributes uniformly from 0 to 1. And we will use this for other for producing other distributions of random variables. And after that, we will use these random variables. We can use only the uniform one, but more for the Monte Carlo method of integration. And first of all, I want to go to the appendix, and only I know if you took a course in probability, so I only remind you that the probability space is a space of three. It's a space of a triple, which is the omega, the sample space, and the f, the events field, and a function p, which is a probability function that meets some conditions. There are three conditions or axioms, the axioms of probability function, and any triple like that is a probability space. So for any given omega and f, I can produce many p's that meet these conditions, and these will be different or various probability functions for this for these omega and f. And you know, if we define the conditional probability, we can prove that this new function, which is the conditional probability of something conditioned by another event, it's also a function that meets the three axioms if the function p meets that three axioms. So it is also a probability space. And I only remind you that x, the random variable, is a function. X is a function from omega to r. That's the reason that I use this. That's the reason why I remind you about this. So if I have an omega, I can assign for each omega in this omega, for each outcome in this space, a real number. So we have here the real axis. But I can assign another number, yes, in another way. And these two ways may be related in some obvious relation or that they are not. Okay. For example, I can ask about the outcome of some experiment and ask about the velocity of a particle. Okay, so I will assign the velocity. I can ask about the same experiment, the same thing that happened, and ask about what? Acceleration. And we have some connection between. Okay. And I can make another experiment and ask about the electric field in the direction of x of the outcome. So this is sum. Okay. I can ask about the electric field in the direction of y, and I can ask about the electric field in the direction of z, and I can ask about the three of them. So it will be a random vector, not a random product. And these two may be related with a connection. So let's call this y, this x. Maybe there is a function that goes from, maybe the x is an invertible function, for example, and I have an obvious function between y and x. Maybe the y, I can write it as g of x. Okay, so remember this x is x of omega. Okay, and we drop this omega because we understand what's the, okay. So for example, we can ask about the two vector the vector of ex, ey, ez, bx, by, bz. So this is a random variable, a random vector with dimension 6. And we can ask about, for example, the electromagnetic energy. And this electromagnetic energy is a function of this. It's only this squared plus this squared over 8 pi or whatever. Depends on the units that you use. Okay, so there is a g of x. And the cumulative distribution function f(x) of x is defined as what?
Integral.
Not the integral. No. It's defined as p. I have p now. I haven't defined what small f is. I will define. P of x is defined as p of x smaller than x. Okay. What's the meaning of this? The meaning of this, x of omega is smaller than x, which means the probability of omega being in the set of omegas that for them x of omega is. Okay, that's the meaning of this. And now fx of x is the differentiation of x. Okay. So I want you to remember that this is a name of a function. This is a name of a function. And this is a name of a function. And this is the differentiation of the function f of x with respect to its argument. Okay. So I can have x and y, and I can, for example, write fx of y squared. Alright. And I can say that fx of y squared is d to dy squared of fx of y squared. Okay. Now this function is a monotonic function. Okay. So it does not decrease. And of course, we have a discrete random variable, and we have continuous random variable. And we can talk about mixed random variable, for example, the amount of rain in a day. So it's somehow a mixed random variable because there is a probability that it will not rain, so it's 0, and then it's continuous. So I think all of this. I only remind you this, so there are many examples in the case that you forgot these things. And now I will talk about this thing of a function. Suppose that we have this function. Okay, we have a random variable x and we have a random variable y, and there is a function between them. And this function is differentiable. And if I ask about the function f of y at some y, if I have a solution of the equation g of x equals y. Okay. So I want to find fy of y in terms of fx. Okay, suppose that I know what is fx, and I want to find fy of y. Okay, for example, this squaring of, if I have x and x squared, and I know what's the distribution function of x, and I will ask about the distribution function of y. So what's the relation between? Can I write something? So the answer is yes. If we have a finite number of solutions or a countable number of solutions for this equation, which are x from 1 to infinity or to some n, and for each one of them, this function, the derivative is not 0. So it is fx of xi sum divided by g tag at x, g prime. Okay, so an example for this, if y equals x squared, so what are the solutions of y equals x squared?
Then the minus x.
Yes, x equals plus minus square root of y, and then fy. And what is the derivative of g? G tag of x to x. And if we substitute this here, g tag of x plus minus, what's it?
Plus and minus.
But they are the same. In this mod, so it is. Okay. So fy of y is fx of square root of y divided by 2 plus fx of minus square root of y divided by. Okay. So you know all of these? Yes, you met them in the previous course?
No.
You proved this or not?
No, but it's a conservation of probability.
Yes, so you call it conservation of of a of probability, and in the calculus language, what's this? It's only a change of variables because we demand by definition, we demand that the integral of fx of x dx equals to the integral of fy of y dy if we are talking about the same region. So here in some region, and here the image of that region. And let's call it A. And the image of this region. Okay. So you can find also a multidimensional version of this. And this multidimensional dimensional version will include here not the G tag, it will include what? The Jacobian.
But it's true because we see that this applies to any region.
Yes.
This is why being.
Yes. And here you have also a reversed version of the proof. We start with f with the cumulative function and prove this. It's not a hard thing. Okay, and you have here examples, and it's only if we can do this, maybe G prime is not zero. So if it's not zero, we go back to definitions. We cannot use this this theory. Okay. So we told you all of this, but I want to tell you also after that here, because we are physicists, we don't care about these symbolizings. And when we say, first of all, this f, small f, we will call it p, small p. And if we write f, the p of x, we mean by that fx of x. And if we write py, we mean by that fy of y. Now here in this course, okay? So p of x, p of 5, if I plug 5 here and here, and p of 5 here, they're not the same. So it's not correct to call both of them p. They're not p. This is the function fx, and this is the function fy. But that's what we mean, and because of this, we can say that p of y dy, which is a function of x, equals p of x dx. If this dy is the dy that is suitable to the dx, okay, so dy over dx is the differentiation of y.
Is there a reason to use the absolute value?
Huh?
Why do we write the absolute?
That's the same absolute value because the integral, the probability function is defined as positive. So if you want, you can check here the proof also.
No, in the sum I get it, but here, dx and dy, dx
Might
be
because dy might be decreasing as dx increases. Okay. Okay, so now also I remind you that, okay, now we will talk about producing random numbers. So the first method of producing these random numbers is using one random variable that we know what it is. It is a uniform random variable, and we apply for it some, or we take it into a function, and then we get another random variable. Yes, so we start with a random variable x, which is a uniform. We make for it some function, and we get another distribution. Here, for example, the distribution of y is not like the distribution of x. Okay, so if we perform a function for a random variable, we will get another random variable that has another distribution function or another PDF, probability density function, and we can use some known method which is called the inversion method. This method is like this. Okay. So if we want to produce a random variable x with a function that is f of x, that's its probability function, probability density function. This f of x I can get from it fx of x out. What's fx from this function? Integral. This is the integral up to x plus from minus infinity of fx of x prime dx prime. So I assume now that I can make this integral. That's the first assumption. And after that, I assume that I know how to invert this, if it's inverted. Okay, so here are two assumptions. First assumption, I know how to write down the cumulative distribution function. Second assumption is it is invertible and I know how to invert it. Okay, if I can do this, I can produce a random variable u, which is uniform, distributes uniformly from 0 to 1, and then take the function of u to be the fx minus 1 of u. Okay. So if you want to generate or produce random variable that distributes with fx, this is a function. So fx is also a function. It's a function of cumulative distribution of this x, but also it's a function. So also this is a function, and I apply this function for my generation of u that I can do using the function. Suppose or assume that the computer can give me uniformly distributed numbers. We have now to prove that this thing distributes like this. Okay, so we have two ways of proving this. By definition, so let's go by definition, or that we use our theory. Okay, so let's go to the definition at first. This variable, what's the distribution of it to be less than some x or smaller than some. I have to prove that this thing is what?
Smaller.
Huh? Capital F x of x. That's what I have to prove. Okay. So the distribution of f x minus 1 of u smaller than x. Okay, and the function f is what? Is monotonic, and it's not non-decreasing. And if it's invertible, so it doesn't have a plateau in some region, in the region that we're talking about. So I can say that this event is the same as the event of fx applied to this is smaller than fx applied to it's non-decreasing function, like e of it, e to the x. Can you repeat that? It's like if you have any function that's not that's always increasing, so x is smaller than y if and only if f of x smaller than f of y. Okay. So f of x of fx minus 1, it's only this u. Fx of x. And this fx, by definition, it's a probability. So it's between 0 and 1. And this u is uniformly distributed. What's the probability of it to be smaller than some alpha when alpha is between 0 and 1? It's the alpha. So it is fx. Okay. And you can prove this using also the theorem. I will give you the chance to do this using the theorem that we wrote. Okay, so that's our way of producing this, and that's a graph that tells you that. So if you have some probability function, which is the density function, that this p is the small f, you have at first to integrate it to get f capital, the cumulative function, and after that, you want to know what is the f minus 1. So you produce a variable u, and this u, you take that the inverse function of f applied to it. Okay, so you produce a random variable u, and then you find the f minus 1 of that. And this number will be your produced number x that you want x to distribute like px. What you want. Any questions? Okay. So here is an example. If we want to produce the or to generate samples of Rayleigh distribution, you remember this distribution comes from what, for example? That the radiation, okay. Maybe it's called because of this. I'm asking about the randomness. So if you have two normal variables or Gaussian variables that each of them is normally distributed with 0 and sigma squared, and they are independent, so the square root of x squared plus y squared distributes like this. Okay. And at first we want to find its cumulative function, so we integrate over it, and its integration is easy because x squared and x dx are related by differentiation, so we can use the change of variables, and the integral is easy. And don't forget this variable. I told you that, for example, it's the square root of x squared plus y squared when x and y are independent and Gaussian sigma, zero sigma squared. So it starts with 0 and goes to infinity. Okay. And what is the inverse function of this? It's easy. So you take -1 at first, and then multiply by minus, and then take the log or the natural log, and then multiply by 2 sigma squared, and then take the square root. So that's the y of u. Okay. Where's the 2 here? Why we don't have 2? Maybe there is a missing 2 here. Yes. So we have to multiply this by the square root of 2. Okay. And of course that if u equals 0, we check the ends of the distribution. If u is 0, this has to be what? 0. That's 0, and the other end is or has to be at infinity. So if u is 1, this has to be infinity, and it is. Okay. Why does it have to be infinity? U is 1. Because we know that this u, when I apply to it f of x, I will get. So I already know that I will get samples of x that is distributed like this. So it has to be infinity. Because x can be infinity. Okay. Infinity, I mean any large number that we want. Okay. Another example is a e to the -x, but x is between 1 and 2. So this a, we have to find it. Okay. How to find this a? Yes. So we compute or calculate the integral from 1 to 2 of this function, and it has to be equal to 1, and then we will find a. Okay, so that's the a. And we find the capital F, and the capital F, when we write down the integral, of course, it's from -infinity to x, but the p before 1 is 0, and starting from 1, it is a e to the -x. And of course, we find the inverse function, and that's it. Okay. So here's also a picture or a graph of the two functions. This is p of x and f of x. It's integration, and that's our way of producing the numbers. So if we take 50,000 numbers of uniform distribution, and after we take this uniform distribution, u, when we get the u, we calculate the 1 minus not ln of this and write down the answer. Okay, so that's x. And another time we sample u and calculate this, and that's x2. Calculate x3 up to x 50,000 and make a histogram. We will get that it's, of course, so approximate or so near the function itself. So this is not, of course, p of x. It is p of x multiplied by 50,000. Okay. Okay. Any questions? So that's our first way. And the second method is the acceptance rejection method. It's an easier method, maybe. So the acceptance rejection method is, I think we have a picture there. If we have, it is like this. If you have a function p of x, then you look at the window that contains it. So that's the window that contains it. Okay. And then you generate pairs of xi and yi. You produce these pairs when this is uniformly distributed between A and B, and this uniformly distributed between 0 and this maximum of P of x. Let's call it M. And uniformly between 0 and M. Okay? So you have to produce many samples of this. And each sample, if the yi, for each sample, if the yi is less than, is bigger than f of xi, you drop it. You reject it. So that's our way. So you sample many points, many points. 1 point will be here, 1 point will be here, 1 point will be here, here, but also here. Okay? But each point that's here, we reject it. And the accepted points, we take the xi's of them. And that's how we sampled or produced many samples of xi that's distributed with this function p of x. We have to prove this, but that's the way. Okay? Any question? Okay. So we haven't proved this yet, but let's see. If we have function 3 plus sine of x, we only produce many numbers or many pairs of x. The x goes between -6 and 6, and the y goes between 0 and 4, and we produce many points, and we reject the red ones here because they are up the or they are above the function. And as you see here, this you can make the integral and show that the efficiency of this is only 3/4, okay, 75%. So it's only what's the efficiency of this? What we mean by efficiency? The good ones divided by the good ones and the blue ones divided by all of them. So it's only the this area divided by the whole area. We can compute or calculate the integral and check that it's 75%. And if the function is, for example, like this, it's very narrow, the efficiency will be very small. Very small. Okay, so we have some problem. We will reject many points, and the efficiency is very small. Maybe we will, or maybe we can fix this somehow. We will see. Okay. So again, when we accept the point, the y is not important. The x is the sampling of the wanted distribution. Okay. And after we sampled many x's, the accepted one we built for them a histogram, and that's the histogram. And of course, 50,000 is better than 5,000. Okay. So, okay. So let's see the proof of this. Okay. We'll not see now the proof because we'll prove the more general. Okay. So again, if this is a narrow function, we have a problem. So we can make some hybrid method. So the first method was the inversion method. The second method was the acceptance rejection method. And now we will talk about some a combination of these two methods, which is called it's not called like that. We can call it the hybrid. So let's take now a break and then talk about this method and prove it. And this method will include our method because it will say that you can bound this function with another function that's above it and then make something. So this is a special case of the general method that we will talk about. Okay. So now let's take a break. No. Okay. So let's continue. Okay. So now our way will be, if we don't know, let's suppose that f of x or p of x is given, but is given, or maybe we know it by some interpolation from sampling data, and suppose that the integration over it is somehow hard, or that if we integrate, it's hard to write down f or capital F analytically, or it's hard to find the inverse function of it. So that's one thing. Or another thing, that suppose that the efficiency is low. So in these two cases, we can use this combination, this method of combination, or this hybrid method that says that if you have a p of x between a and b, that's p of x, you can find another function that you know how to integrate over it. Okay. For example, this function. This is a function that I know how to integrate over it. But this function, of course, is not a PDF function of some variable. Why?
It's not very like.
Because the area, yes, the area is not. The area is bigger than one. But what's nice, what the condition that I demand here is that at each point x, this function is above this. Okay. So this function will be, of course, some c multiplied by function for another variable. Okay. So the integral of p of x dx is 1, from A to B, but also the integral of f is 1 from A to B. And this function, I know how to find its CDF. Okay. Or the integral of it. So our way is like this. Yeah. Okay. Okay. So now we will produce many variables, many samples, u and x of this f. How to produce x of this f?
Inverted.
Exactly.
The same method as before.
I wanted to say the u. Exactly. So how to produce x of this f using the inversion method. So this is the inversion method. And this is only sampling a uniform from number from the computer. And this is from 0 to 1. Make the uniform. So we produce many samples of this, and we reject the sample if the u multiplied by c multiplied by f of x is less than p of. Okay, so yes, if u multiplied by c multiplied by f of x, all this u0 and x0, u0, x0. If it's bigger than p of x0, we drop it. And the values that we will take at the end are the values of the x's that were not dropped, or in the pairs that were not dropped. And the u's goes away. They go up. Okay. So how is our previous method is an example of this? What's our previous method? What's the f in our previous method?
For previous sum of x.
We draw a rectangular here, yes?
Ah, okay.
That's our f. That's our c dot f. So what is f there?
Constant of 1.
Constant. Say uniform. So
c minus f.
our previous f for the acceptance and rejection method was 1 over a minus b from a to b. That was our f. Okay, so the f was 1 over b minus a from b to a and 0 otherwise. Yes. So what was our c? We multiplied f such that this point, which is this, will be c, will be the maximum. Okay. So c multiplied by b minus a was the maximum. So the C is B minus A multiplied by the maximum. Okay. So that's our previous method. And now we have to prove that this method, of course, gave us what we want. So we want to calculate the probability that X that we got it is less than something. Okay. So if we sample here X and we accept it, what's the distribution of it to be smaller than something? Okay, what's the probability of it to be small? And we want the answer of this to be what?
B factor B or
Yes, the integral of this. So the probability of accepted X to be smaller than X. So it's smaller than X. Condition that we accepted it. Or known that we accepted it. So the acceptance of X0 is when U is less than this. Okay, so U is less than P of X divided by. Okay. And what's so use by definition, this is the definition of a conditional conditional probability. And what's the probability of X to be smaller than X and U to be smaller than P of that X? Okay. How can we compute this or calculate this? Knowing that U and X are independent. So can I multiply them? Or what?
they're independent.
They are independent. So can I
But the right one is a function of X0.
So I cannot do it. Okay?
They're not independent.
These U and X are independent as variables. So if I ask about X to be smaller than some given number and U smaller than given number, okay, I can multiply because these two variables are independent, which means that these two events are independent. But these two events are not independent because X also appears here. So I have to compute or calculate this using what? Yes.
Complete.
Yes, of course. And we add this condition and multiply by f of x cubed. And this f is the function. We already know that this our way of producing x gives us an x that is distributed with this small f. Okay, so this is also a PDF function for some distribution, and we can calculate using it. And now, after we fixed what x0 is, now these two events are independent, okay, in the integral, and we can multiply them. So this will happen. Now these are numbers. These are numbers. Now this x is a number, and this is a number.
Oh, so we simply demand that they are both smaller than some value, but not.
Yes, for example, if x and y are independent, and I ask you, what's the probability of x being smaller than x and y being smaller than x squared?
Yeah, okay.
It's not the multiplication of these. Okay? Because I don't know what is x here. X smaller than x, maybe it is the half of x, and then the y will be the half of that x squared. So this is the integration f of x of this, given that x equals x, 0, that let's say. And
Yeah, it's that.
when x equals x. Okay. Now, what's the probability of, first of all, if x equals x star, so y, I can write down here star, and I can write here also.
So because they are both rolled independently, it does not matter that they correspond to the same value. Okay.
So this is now a multiplication, but what's the probability of x star being smaller than x? We integrate, of course, over x star from minus infinity to infinity, or from a to b here. Here it's from a to b. So this is 1 if x star is smaller than, and it's 0 if not. Okay, so if it's 0 if not, I can drop this and here. That's okay. And I will be left with u is smaller than p of x0 over c f of x0 multiplied by this f. And this is, of course, because this is smaller than 1, it is the same thing. And now it is the integration over p. So that's it. Okay. And I have 1 over c. I have 1 over c. Yeah, what?
I is supposed to be an indicator function.
Yes. It's 1 if it's true, it's 0 if it's not. So this is this probability, and I will have to divide it over this. So now I will integrate over x without this. Yeah. So if I integrate over x without this, what's the answer? So I will not have here x, I will have here what? Infinity. So what's the integration to infinity of this?
1.
1. So it's 1 over c. So it is this divided by 1 over c, which is this. Okay. So I got that my accepted x, its probability to be less than some given x is the integration of p of x up to it. So that's what I want. Okay. And here is an example of this method. So if I have a distribution function that looks like this, of course I have to to normalize it. But anyway, we can drop these constants and think without them. And I cannot integrate over this function and find capital F and find the inversion of it. So I bound it by the function e to the minus x. This function, I know what it is. And you see here that our efficiency will be not so good, or that is good. For me, this will be good, but maybe smaller than half you will consider it's not. So all the points that we will generate here and here and here and here will be dropped or rejected. So here is our acceptance rejection method, and this is our new method.
So, is there a way for us to find this out? And do we need to specifically for each problem?
Of course, this f is an f that is above the function, and you know how to integrate over it and find the inversion of that integral. Okay.
Oh, is there a formula for it?
No. Of course not.
Do we know the PFX, the Lay's probability function?
What do you mean?
Because
That's P.
we know it's for the
This is
sentence or reject.
Okay. No, so this is P of x, not that's P of x up to a normalized.
You know it, why can't we just bound it with our probability with PFX? If we know already the array function, why don't we just use it and not some arbitrary function?
You say that if I use the function itself,
I want.
I will not reject any point. I will not reject any point. So of course, okay. So if you know how to compute the integral of this function and find capital F and find the inversion of it, so do it. You will not reject any function, and it's our inversion methods. It's a method that we use, many use, and perform for them f-1 to them, and that's it. We don't reject it.
Simplicity.
Yes, not only simplicity, you cannot do this. Try. Okay, and of course the efficiency here in our new method is better than the previous one. It's 40% compared with 25%. Okay, any questions? Okay, so now we'll talk about Monte Carlo integration. And the Monte Carlo integration is a simple way of integration, especially with multidimensional integrals. And it's so simple and easy. Not so. So if we have, for example, a particle in 3 dimensions, and we want, for some reason, to integrate over the space of it, we have an integral of how many dimensions? 6. Okay, so we have integration over x, y, z, and px, py, pz. And we want to use our previous ways of numerical integration. We have integration of, for example, in 3 dimensions, x, y, z, over some space or region in that 3-dimensional world. We have to divide this to many segments, and this to many segments, this to many segments, and find the value of the function at each small box. Okay, so here we'll have the small box, and here we will have small box, and I have here f of xi, y, j, z, k, and I and j and k independently run from 1 to n. Let's say that I might make for all of them a segmentation of n points or n segments. And therefore, the points, the number of points that I take goes like n cubed. So that's in 3 dimensions, and in 6 dimensions, it's n to the 6th. Okay? So our integration methods will somehow have a very large complexity if the dimension goes if the dimension grows. And the Monte Carlo method says that we don't take n, and then n cubed. We only take n, and this n will grow, of course. I will take more and more quantity. But for each n, I sample an x, and sample an y, and sample a z. Okay, so I take n random points in this box. That's the okay. I take n random points in this box, and I hope that if I sample many points, the average of the function at these points will be the integral up to that value, the volume. Okay, so here are all that. Let's take it in 1 dimension. So here's it in 1 dimension. If I have an integration over f, I can think of this integration as the average of f at many points. Okay, and I can hope that this x, which is this x, of course, I take it as uniform between a and b. Okay, this x is uniform between a and b. So suppose that x is uniform between a and b, and I ask you, what is the expectation? Okay, the expectation of x. You know this, yes? So what is the expectation of it? The expectation of x, if I take it uniformly, it would be a plus b over 2. But if I ask you what is the expectation of f of x, what's the answer? It's the integral over f of x dx multiplied by the PDF function, which is 1 over p minus a from a to b. Okay? Now I know that I can, using the central limit theorem, I can find this by sampling many x's. Okay? Only take many x's and find this. So if I take many x's and try to find this, it will be what? The sum over f of xi. I goes from 1 to n, 1 over n. Okay. I know that if I sample many x's, this will go to the. Okay. Therefore, the integration, this integral is the length of the domain that I want to integrate over it, multiplied by the average of f at sampling points distributed uniformly in the region. Okay. And as the central limit theorem tells me, it's without the central limit theorem. So theorem before, the difference between this and this will be what? The variance. I call it the variance. So we write here what I say, that this integral is the length multiplied by the average. If it's d-dimensional thing, so it's the volume multiplied by the average. Okay. For example, in 3 dimensions. And our variance or our standard deviation goes like this, and it always goes like 1 over the square root of n. It always goes like, okay. So that's why the Monte Carlo method is good, because our previous methods will grow with adding more and more dimensions, but the Monte Carlo method always behaves like one over the square root. So let's take an example. Yes, the trapezoidal method, we know that it goes like h squared. Yes, if we add more and more points, so it will go like n to the minus 2. So if we have 4 dimensions, okay, if we have 4 dimensions, or d dimensions, the trapezoidal method will be n to the minus 2 divided by d. That's because n is like L over H to the power of d. Okay, so this n now is the n squared here. So let's call this n. Okay.
So in the end, the big N is the number of sample points.
Yes. So yes, the big N is the number of sample points. So here it's n cubed. So if I want to use Monte Carlo with n equals, for example, 64, here I sample 64 points, and here I divide each one to 4. And 4 cubed is 60. Okay. So if we use the trapezoidal method, we see that if d equals 4, it will be like the Monte Carlo. It will go like the Monte Carlo n to the minus half. And this is the critical power, and this is, or the critical dimension, and this is called the curse of dimensionality. which means that for any segmentation rule or any integration rule, numerical integration rule that you will have for it a critical dimension above which Monte Carlo will win. Okay. Yeah.
Does D always enter like divided by D the ever, for example, in the Simpson? Normally it's 1 to the n.
You always, yes, you always use this key, yes.
So
because
Simpson is proportional to n to the -4 divided by D.
because n here goes like n here goes, it is equal to n to 1 over d. Okay, that's it. Okay, now if the region is not this, if the region is this, that's the region of integration. Let's say that's the so if we have a nice way to sample these points in a uniform distribution, so okay, it's okay. But if we don't have, what's our method? Yeah, it's only to reject. Of course we can, if you know how to put something over it that contains it, and you know how to calculate everything, it's okay. But the simplest way is to take a box that contains it and use the rejection, the acceptance and rejection method. So our alternatively, we can define f, which equal, if I want to find the if I want to find the integration over some v, I can define f as g if my point is in v, and I define it as 0 if it's not, and then I calculate the averaging over f. When I reject some point, I put it into the average. Okay. So this way can help you, of course, to find volume of some rigid body or a mass of that body with a density function. And of course, the center of mass, you will have this in your homework. Okay, I think so. Let's see here. Okay, so here you see an implementation of the acceptance rejection method, and the important thing for you to know is that you can use this random to generate random variables, and if I want to if I can generate a uniform variable from 0 to 1, how can I generate from A to B?
And A and
using only a linear transformation. So I don't think there's something important here to say. So that's it for today. Any questions that you want me to make this bigger?
So the Monte Carlo integration method helps us find the volume of multi-dimensional.
Not only a volume, it helps you to find the integral, the multidimensional integral over a function. If that function is 1, that's the volume.
Also probability.
Hmm?
Also probability.
What do you mean?
Like if we want to distribute points space,
Okay.
so can use Monte Carlo.
Again, what do you want to do?
To put some random points in a specific area.
No, for that we learned how to do it. Okay. So we learned how to do it in 1 dimension, but you can use a version of 2 dimension of it or 3 dimensions. The Monte Carlo method is a method of integration. Okay, you have to remember that. It's a method of integration using random variables. Okay, but it's a method of integration. Okay, so see you next